Hi everyone. My name is Mohammed Shahbaz. I'm a professor at University of Michigan, and today I'm hosting a recorded P4 workshop talk by Jitesh Nambiar. So Jitesh Nambiar is a PLM architect with about 20 plus years of experience in PLM strategy, M&A, and system integration across high-tech, retail, and aerospace manufacturing. His background is in mechanical engineering from the University of Mumbai, and he has worked with several Fortune 500 companies like Apple, Marvel, and Intel. So, with that, Jitesh, over to you. Take over.
Thank you, Shabazz. So today I'm just going to discuss about AI-enabled BOM lifecycle for P4 programmable infrastructure reliability. So as Shabazz, you mentioned, I have my background in PLM, product lifecycle management, and out of the many different areas that we have done, some of the areas are around the data center infrastructure and the service bomb and the other details comes into play, and one of the use cases was around the P4. So just to give a background about the evolution of network infrastructure, as we are aware, like the traditional networks always had the static configurations, and users have to manually provision. The maintenance was reactive, and there was very limited programmability capacity. And then the P4 programmable infrastructure got introduced, and with the advent of P4 programmable structure, we have this dynamic data plane programming concept, and where you can have software defined behavior using agile framework, automated deployment, and enhanced flexibility. However, this newfound flexibility is not without its cost. Before, for all its logical elegance, are uh, ultimately executed on physical hardware targets like the ASICs and FPGAs and SmartNICs, and they are subject to a wide array of failure modes, right? So the reliability of the P4 network is therefore not merely a function of the software correctness, but is deeply intertwined with the physical integrity of the underlying hardware, right? And hardware failure does not violate the P4 language specification. Rather, it breaks the physical contract upon which the language execution model implicitly relies. So even the most advanced programmable data plane requires predictable failure management and consistent provisioning to maintain the service reliability. So this paper session talks specifically around that area, right? So what are the challenges in the reliability of programmable networks, right? So the P4 programmable switch is fundamentally constrained by reliability of its physical components, even though the software layer manages all the data planes, but it is still running on the physical component. And there are hardware failures, as we are aware that they fall into classes like overt failures or covert failures with the fail stop or the fail corrupt model. And traditional reliability approaches really fall short here when applied to the P4 backed infrastructure. So we need a new methodology for uh, network engineers and architects to kind of make sure the reliability is good for this kind of networks. So that is what we will discuss more in detail here, right? So we want to introduce the AI-driven service bomb methodology, right? Uh, its foundation is based out of service bomb. Just a background on service bomb. This is something that we use a lot in the product lifecycle management domain, and it has been in existence since a long time, and many companies adopt it. So, and the way to manage service bombs really depends on what kind of. If you look in a data center, you have this large cooling equipment, so they are managed differently. The rack and servers and the trays and components are managed differently. Some use product family level service bomb management. So that underlying framework still remains the background for basis for this discussion. And under that structure, we are going to make sure that the P4 switches are managed in a way where we can improve the reliability, right? And then to add to the mix, we have this AI powered intelligence, machine language is very powerful these days, and we can generate models that can predict failures and optimize provisioning and lifecycle management decisions based on historical patterns, based on the data that is fed. And for P4 adaptation, P4 comes up with its own APIs, which is one of the advantages of going with the P4. And we want to kind of bring that to the mix with the foundation of the service bomb and the AI powered intelligence. So that's pretty much what this framework is about. Um, so breaking, how do we make it happen, right? So breaking the infrastructure into manageable, trackable components will enable our better lifecycle and prediction management, right? So we need to modularize the components, and each component can contain its own reliability profile and dependency mapping. And the second one is a FRU-based approach. Again, FRU is something, again, pretty much in the reliability space. We call it the field replaceable units. And as part of the BOM data model, we need to have provision to manage this FRU information. A good example of FRU is it kind of lets us know that when in the field, for example, are you going to replace the whole switch or any component underneath that, right? So that is a demarcation which this through gives. So in this context, it helps us identifying the assembly or the switches which is where to maintain the discrete flows, and we can implement the predictive replacement schedules for this discrete flow. So that is, we will talk about the framework towards the end, but that is again a very key important aspect of this strategy, right? So that's pretty much what the component modularization and the free braced approach talks about. Um, so what are the enhancement that we will do through this modular design, right? So there are some key steps that we are required for modular design are define the classification for components. You need to catalog all the pre-for programmer elements with some reliability characteristics, failure modes, and their interdependencies with the infrastructure stack, right? So we need to break it down and have this classifications. Secondly, define the dependency mapping. We need to establish clear relationship between the hardware and these components of the P4 program. I mean, there is industry talks about the application lifecycle management (ALM), where manage the programs along with the bill of materials. So leverage those concepts here. And then the life cycle integration, right? So align the when we say talk about life cycle, there is a component life cycle. So whenever the replacement cycles that you need for a component, you align with the P4 program updates and maintenance window. This helps us reduce the disruption and have faster turnaround for any of the changes. And lastly, automate the whole orchestration, and again leverage the statefulness of P4 and the APIs that come with it. And this whole orchestration is possible where the whole component lifecycle and the P4 states and the service continuity can be managed. For example, ensure that the network has some redundant path for all the traffics to flow while the line cards are getting changed, and so on and so forth. Right. So that is uh, another key aspect of the modular design that we talk about. Moving on, uh, predictive models, right? So AI-powered predictive models, they analyze the patterns across the different device telemetry that we have, P4 execution metrics that we have, and historical failure data to forecast some potential issues that can happen before the actual impact happens, right? So the models are getting very powerful these days. So the more failure prediction is possible, the algorithms can be tuned, and it's a mix of the environment data, the telemetry data, and the P4 program behavior to identify the devices when they are approaching the failure threshold. So those are failure predictions that we can provide, and this can enable proactive replacement even before any actual service disruption happens, right? So that's somewhere this AI powered predictive model will help and ensure that the models are trained optimally with sufficient training data, and they need to be trained for overfitting and for any biases and so on and so forth, right? And that is a standard pure play standard AI machine learning mechanisms, which is not very specific to this, but that's the standard process out there. And then it helps determine misconfiguration, right? AI models trained on the correct P4 deployments can proactively identify when a subtle misconfigurations that might not trigger immediate failures, but could cause future reliability issues. So predictive modeling really, what will happen with the infrastructure, that is where this model really helps. Finally, uh, the core advantage I keep calling out the which is the P4 control APIs, right? So it provides direct integration, runtime integration with the P4 APIs, and then providing an orchestration layer. That's because we are talking about the BOM data and then the telemetry data which is coming on from the field. We need some orchestration layer where the BOM life cycle systems and the P4 plane operations can be coordinated. So there are many kind of tools that are available, middleware, and they can manage this information back and forth and the traffic. And finally, the automated provisioning, which we spoke a little bit in the previous um, slide. It helps streamline the deployment process, and it helps both the hardware provisioning, and then let's say you replace a new hardware and you want to install the program when after replacing. So all that can be automated and orchestrated. There are some SDN controllers which can give those signal, and I mean, even the P4 needs to be still installed on your new ASIC. So that is where this orchestration, automated provisioning comes into play and helps with it, actually, right? So um, now, what are the core components? I mean, we did talk about this in the previous slides, and just wanted to summarize, right? So the core components are the P4 control APIs, like the program forwarding, which we also discussed about. BOM lifecycle, it come from the PLM data and the modular components that we discussed about. It can provide inventory and lifecycle tracking. So if a component is reaching its failure, or you can track whether there is inventory on hand. AI models, so it can forecast the failure and the capacity needs based on the model that we discussed about, and provide some predictive modeling. And then hardware monitoring, right? There is already telemetry and health signals we already have to check whether some ports are active through the LED lights, and so on and so forth. So that already exists, the telemetry and the hardware monitoring, and that can be kind of bundled into the whole architecture. And finally, the automation is the where the deployment and the configuration, and if you can route the traffic to other line cards while the change is happening. So that automation. So these are the core components of provisioning automation framework, and the unified control plane ensures that there are consistency between the hardware and the software life cycles across. So those are what are the bare bone components that are needed to ensure that you have a fully working automation added to the whole architecture, right? Now, what are the benefits? I mean, after doing all this thing, what we will benefit, right? So this model will help reduce the onboard friction, right? So it helps in reducing all the manual configuration steps. We did talk about the automation and potential any human errors that will help us streamline the deployment. So that's a key advantage with this model. And the other one is we can improve the uptime, right? Another benefit of this predictive failure management is reducing the unplanned services in the context of P4. I mean, it can be expanded to other components of the data center, but just in the context of this P4, all the related issues and the mean time to recovery can be improved. And finally, in cases, let's say there is an error that has occurred, it can help with some faster root cause identification, like why did it fail, and then automatically provide recovery procedures for us to uh, kind of replace and recover faster from the incident that is there. So those are some of the key benefits of the model. Moving on to the implementation framework, right? So I mean, just wanted to say that the framework only improves and gets better as more and more data is available, right? So we need to assess what is your infrastructure and the plan. Um, Always better to start a pilot deployment with a particular location where there is, let's say, good redundancy to manage the traffic and the impact is low. So start with a pilot which is which has a contained blast radius, if in case when you're trying a new model, and then learn from the pilot, and then scale and optimize, right? And refine the model based on the learnings, and finally we'll say rinse and repeat, right? That's the continuous improvement. So keep enhancing your accuracy by, I mean, as in where more and more deployments start using this, the data and the accuracy is only going to go up, and the information is going to and we can always find this 1% improvement and continue to improve on any um, efficiency or accuracy pointers around that, right? So that is a brief about the implementation framework. So who are the main beneficiaries, right? It's mainly the network engineers and the architects. So it will help in reducing some of the emergency interventions that is usually happens on site. So it will definitely help the engineers eliminate that. And the automated task also eliminates configuration task, right? So we did talk about there is some manual humans involved. So when you have automated provisioning, that can eliminate some of the repetitive configuration tasks. And AI-driven insights enable the proactive infrastructure optimization, right? So this data-driven approach provides measurable improvements in the operational efficiency. So that's what the benefits we get for the network engineers out of this, right? And platform architects also can gain comprehensive from the tool for scaling the deployment. So the same benefits apply for them as well, right? So how do you start with this? I mean, just to summarize the whole discussion, this of methodology offers network engineers and platform architects a way to scale and automate the P4 infrastructure reliability. So the key components is start with the modular BOM strategies, augment your already existing service BOMs that you have, and build your structures that can help you identify the fruits and dependencies with the mapping between the software and the hardware. Um, then implement the AI predictive models. They can happen in parallel because they are not dependent on each other. The predictive and models are based on already that is information that is available, and then integrate the P4 APIs with your lifecycle automation. And this is like the foundation for sustainable and high performance networks that is available for the P4. So that's in short a summary of what this whole framework provides, and yeah. So that's pretty much what I had to discuss.
All right, no, this is interesting. So, yeah, so I think maybe one thing we can spend some time on, like, is so you mentioned like implementation and the establishment of the framework. Is it like you're setting up the blueprints for what is there, or is it like there is an actual implementation of this sort of process that you talked about already
Yeah,
there?
it's a blueprint. I mean, as I said, in some areas it is there, like AI models are a standalone, right? The predictive one, and maybe orchestrating all together. It is we are slowly getting there. It is not something maybe done in exactly all of that, but the modeling of the BOM and the AI, this is a framework actually which is there, right? And it can be implemented, and we're we eventually
Right,
will get there as models getting better. And the advantage of the APIs, right? I mean, what is limiting was that how do you stitch all this together, right? Because you
yeah,
can build the bombs and the ALM already exists, but they are like traditionally PLM was there to manage for like if you have a software release going along with the hardware, it's already enabled and capable to do that. So yeah,
yeah,
that is where you can kind of bridge that
okay,
in. So those are individual modules and concepts, and they can be stitched together.
yeah, okay. So the other thing I think like the focus of the talk was mostly on reliability, like how do you enable that across these layers?
Mhm.
Is there a notion of time associated with it? How fast, how quickly? Is it like in seconds, or do you need to react at line rate, or do you need to do something in middle? Like, is there a notion of time associated with these recoveries for the reliability you mentioned?
Yeah, I mean, typically in some cases in the manual one, it usually it can take weeks actually to go the manual way, right? And this can definitely. Reduce it to days with the fewer one, because first is you can prevent the whole damage from happening, right?
Right.
And I mean, there are different dimensions to it. So let's take one is the, if you time your component change along with the updates, right? So then you don't need to take two different outages to manage that, right? So in that case, there is definitely this understanding that, timing it together, definitely there is an advantage. Secondly, in the configuration, you have the setups that are needed, the manual tasks that are needed to configure it, and the orchestration can really bring those repetitive tasks. You can do that, like to route it on your other network, replace the component, and then start the installation of the program or the people program on the component, and then make it available. And while the disruption is minimal, so
Interesting.
those can be is where the advantage really falls on.
Okay. So I think the other thing interesting was here was like you're basically touching upon three axes, right? Like one is flexibility, which you get from P4. The other
Mhm.
is the what you want to achieve, which is reliability. And then you are bringing in this sort of the AI-driven BOM mechanisms and strategies, right? Like how, so the question is like, how do you achieve like so the goal seems to be like you want to combine AI driven BOM strategies with the flexibility that P4 gives you to achieve reliability in some sense. Like do you have any concrete like sort of like ideas on maybe a use case or something that actually elaborates this more?
Uh, let's say, put it together. The bomb is an existing constant. It doesn't exist, right? We do put it like a switch, actually. Like, we don't break it up to this level of component, actually, where, let's say the easiest way is I'll replace the whole switch, actually, because, it's difficult to manage, right? In this case, we break it up based on what is the component that can be replaced without completely coding the switch as a black box, right?
Hmm.
That is that level from the bomb, right? So that is a data model that I was talking about, and the stitching that what is the through is really needed in that area. Right? That's one aspect of it, and then augmenting it with the middleware that you can connect with the telemetry information that is coming from the air, right? Because just saying that the whole switch has a problem is going to be difficult for us to kind of maintain that. So that
Right.
is the intersection where this is kind of trying to bridge that gap together. And can we do this with traditional networking? Maybe different. You can just use that, but you don't have those APIs coming up from the P4, which is what P4 additionally provides.
Right.
And you can know from which data plane, where in the back plane or wherever is the issue, we can maybe isolate and get to that kind of level. And that is where the AI comes into play because of the telemetry. And how do we inform? I mean, there is a lot of information to mine there, and
Yeah.
then how do we kind of bring it and use that actually?
Interesting. Interesting. Okay. So I think continuing slightly more on this conversation. So um I think the point here was you so you mentioned like so we are applying so you have the flexibility of P4 and is it like switch local or are you like when you think of AI driven BOM strategies are these switch local or are these like data center level or a network level are these encompassing multiple switches
Yeah,
and working with them or is it like more of a switch like from a single switch point of view that you're
that's a
looking at? Yeah.
good question. So when you get into the let's say from the bomb is like a single, it doesn't instantiate, right?
Yeah.
But when you get into the service model, you get into an asset level actually, okay? And that information is translated to the asset because when you said the switch is local, every switch is identified as an asset in this. Like let's say
Right.
I have say 50 switches needed in a tree. I mean, this is not the right number. You don't have that many switches, but let's say one switch in a tray, just giving you an example. But it might be there are 100 trays there. Each of them are its own individual asset, actually, right? So that information is very localized to that. But the
Hmm.
the data model is the common actually because every tray has to be built with the same data model. But the information is local to that particular asset actually. So obviously, when we talk about BOM, there is an asset level BOM that also goes into it. So from PLM, we give this framework, which is like the data model, and then it moves on to individual serialized assets actually, so that you can because you really need to know where it is failing. Otherwise, there is no kind of advantage to it actually. So,
Right. So what kind of like improvements can we anticipate in the uptime and onboarding of these things? What level of improvements should we anticipate if we do this thing in our
yeah,
environment?
so one is definitely reducing the unplanned downtime, right? Because sometimes depending on what is the issue, right? I mean, if, let's say there's a cooling problem and something fails, sometimes it might be very localized to one or two ports and you might not bring it down, but it really depends what kind of failure happens, right? So when we talk about what are the improvements when we say uptime, just taking a very uh, use case by case basis, depending on what is the failure, we can uh, reduce the time downtime because this is getting a signal that something is going wrong there, and either do a proactive replacement before the whole thing comes down, or first thing, let's say it really hits it and you're not able to catch it, the installation and the automation can help you replace it faster. So that's the other part of the downtime, right? And then the third one is proactive maintenance, right? So you can plan this with your software updates together, so you can bundle them together, and then that can be saved in that aspect.
Okay, okay. All right. So I think to close the talk off, maybe one last question. So again, this whole framework that you talked about. So for any organization that is just starting with their P4 programmable switches, what do you think is the first step for them among the various steps that you mentioned in your talk?
Yeah, I mean, as I said, always start simple. That's what important. And it's not that you achieve all of them together, right? First is the modularization of the P4 components, as I spoke about, right? Using whatever the BOM methodology we were talking about. Like I can't have it like a black box. You have to break it down to the component where you can really map it with the P4 program and software, right? So for identifying the flues, and that gives the visibility to your structure. And then is the next layer of the predictive model that we build to anticipate the failures. And once these foundations are in place, then we can integrate the P4 control APIs with the lifecycle automation systems, and then unify the software and the hardware together. I mean, all throughout we're talking about this layer of software and the layer of hardware, and just trying to
Yeah,
how to bring them together. And this approach has been tried, as I said, if you bundle, let's say, ship a product. Actually, you take your iPhones or whatever it is. It comes with the software, and there is a software has its own version, and the product has its own hardware, and how their compatibility to it. We call it ALM, application lifecycle. And I'm just trying to bring that from a larger set to a very focused area that this is possible actually to do that, right? So, and each steps adds reliability, and but the bomb is the more foundational one here, because if
yeah,
without that you will not be able to identify and get the advantages, because each of them are running. It's not that there is no telemetry already in this field. Everybody's doing that. It's another use case that you can use this information and integrate it and bring it.
interesting. Well, thank you so much for taking the time and talking to us
Oh,
and
my pleasure.
sharing this talk. Hopefully, we'll see you again
Yeah.
virtually at the event at some point. So, yeah, thanks
No, it's
again.
a pleasure, and thank you for having me with this esteemed forum. And thanks again, and good luck with your whole event that is planned out. Thank you for organizing. Thanks, Dennis and Shabazz, for your time.